Hi, good day. And now we're starting again with another chapters of our episodes by Silvanus P. Thompson on his book Calculus Made Easy. Now we are here now in chapter 3, but before we go on this one, I request everybody to subscribe and tick the bell and notification here in my YouTube channel, Enercon World Explorer TV. Now, okay, let's go here. Chapter 3, what we have here is on relative growth. So we are expecting how the subjects will fall on. Then there's a ratio in that. Then we will be introducing to you the subjects that we will be talking to. It's about how we classify on them. So let us classify on the subjects that we will be dealing on that too. Class, we have here number 1 is the fixed. We have here the constant. And number 2 is the variable. On constant representations, it would be represented by usually by the beginning of the alphabet, usually the first 3 of the alphabet. We have here symbols. We have here A, B, and C. Other reviewers also, they are representing M, N, O, Phi. Now, for this constant, they are fixed value. It means to say, it has a value already. So when we say it's 1, it says there is a particular value already have given in a particular issue. It is fixed already. Now, on the variable side, we have here our presentation is the last variable of the alphabet. We have here X, Y, and Z. It could be represented also with another letter, U, B, W. Take note for electrical practitioners. These are representations of the letter are being used also for the terminals of the motor terminals, U, B, line 1, line 2, and line 3, excluding the neutral side. Now, it could be represented also by letter T. Okay? Now, we would expect this one that there is proportion for that. For X and Y, they are dependent of each other. So we'll be talking about on the relative growth. So we'll be dealing how far we are going to alter them. So we are talking about the variables. So when we are talking about the variable X, Y, and Z or Z, we are talking about how far we can alter them, we can change them at a particular time. So at particular portion, which we meant to say that we will be involving how to get a comprehension by making a little bit. Have you familiar of this one? On this letter, it's D. It's not a particular D on this one. It is an element, no? It is an element. Mathematical says it is an element. So when we say you have dy or dx over dx with respect to x, or with respect to dy over dx, when we are making comprehensive differentiations of that. Okay? Now, let me take 2 examples for that, so that we will see if we are going to increase the value of x, then y also will increase on that also. So let us see this one, because momentarily it would add also in our analysis once we have in our calculations. Very important for us to get a comprehension on that. So, take for example, say it on your mind, and that d is a little bit of that portions of x, and a little bit portions of y. When we say this one in derivative, c dy over dx is a little bit something on that. Okay? Okay, listen that. Let me say on the sample one. Okay, sample one. So, for example, if we have here a rectangle on this, we will see that this is the y, it's the height of this, and this is the x on the base. And for example, if we have a tangent for that, theta for that, for the angle, it will correspondingly, this is the right angle. This is the right angle, 90 degrees. So, for example, this is 30 degrees on that, and we have also 60 degrees on that. So it would be a right angle. Now, numerically, on the analysis, we could say that if x, y on that, for example, on this 30 degrees, even with a particular value of that one, we can make a changes for that one. If we will alter x, y also will commensurate on that. Proposing this one with the same angle, even we will have to put this one here. Now, in a projectile, let's say for example, if you are playing with a soccer field to this one, you will see this one here, a ball, kick it out to the net. No, this is the goalkeeper on that. No? If it will go short to this goalkeeper, it particular motion, no? A motion, a particular projectile motion on that one. So there is a release of this one for gt squared on the accelerations of the ball if you are going to put this one. Now, if you will ask of the ball how far this one here, even at a distance of this one of how many, and that we will dealing this one. Supposing this was it's a plain ground on the plaza, the soccer field, we will see this one is 5 meters. We have to go, and it is 3 meters on this one here, on the y-axis. So this is 3 meters. You could see how on this ball will go short on that particular. We will see how. So on this one, we could get a portion of that. How the ball keep rolling on that. Okay. So on relative growth, we will see how x, a little bit of x and a little bit of y, we can add of that. We can alter this one here. Is this a particular? Are they proportion? Are they in proportion if we will alter one way or another? So as we go on further, we will see what is the ratio of dy over dx. Okay? Now, let's go on the other sample. In a particular construction work, in a construction project, I will see let's apply this one here. We will apply this one. A particular electrical technicians would like to install in a particular substations. So this is the. So he will install these electricians. This is the accept light. or wither fruit. Oh. Wither fruit. Light. Okay. This is a lighting. Now, in this one here, we are going to measure this one here. This is the wall of the substations. This is substations. This is power substations. Yeah. So if this is the emergency light, the electrical technicians is going to install this one, and with going to install with the use of a ladder. For example, this is the ground. Okay. Now, at particular distance of this one here, supposing this is the X on this. Say this is the tip bottom of the ladder. We have getting this one as A, and the upper of that one on the ladder, which is the on the Y side here, where this is the ladder. Okay. So this is the foot of the ladder. So if this one is 3 meters, and the Y is also is 4 meters. So we know that when we analyze on that in a particular triangle on this here, if this is X, if this is dy, the corresponding of this one here on this portion, we will see how the dy corresponds. So this is the dy. If we will add this portion, so this is dy, and this is the dx. For example, if this one 3 meters and this is the 4 meters. Now, if we are going to change it again, because according to the plan, there is abbreviations of the construction, approved construction drawing, and the supervisors, the engineer and supervisors instructed again the electrical technician to change the setting, to change the positions of the emergency light, so that he can install this one. So let's say on this one, for example, if we are going to put increase x plus dx, we're going to put a portion of x with 1 meter. Suppose now a y also, y plus dx will correspond to that one on at ordinary time without changing. But if there is a change already, then that that particular 4 meters will reduce. So let's say, for example, if you are going to get a 1 meter additional for that x, or then we could see the expressions of this y, 2y minus dx. Okay. Example, if we are going to get let x be 3 meters and y also 4 meters. Okay. Now we are going to answer this one. We are going to answer that one in a formula. So we will solve this one, the length of this one, in a formula. So Uh, have you noticed on this? Because this one here, if you are going to move on this one, the original, then the ladder is going to move on this portion a little bit something on this. Now if you are going to move 1 meter on this, so if the dx will move something with 1 meter, we will also meet depreciate, will deduct also dy something. So this we don't know yet. Okay, so that is dy. So this one here is the proportion that if you will put this one here, this is the proportion of dy and this is the proportions of dx. Okay, now how are we going to solve on this? Okay, let us solve this one in another theory. This is what we call Euclid I.47. So it is coming from the book of the elements of propositions by Euclid. He is considered the father of geometry. Euclid. This is way ahead from Pythagoras. But you see, there is an influence already with Pythagoras on this. On this writing, there is a collaboration, so it depends upon a debate on this particular theorem. Now let us see on this one. We are going to determine this one on this particular issue. How we are going to determine the length of this. Because let us see if this length of the ladder is equal on the other side. Let us see, because in plain trigonometry in plain Pythagorean theorem, you will see on this one here only. Okay. So let's say this opposite and this one here and the hypotenuse. Let's see in this one the sequence is the hypotenuse is equal to the square of both sides. Okay. Okay. So with a particular angle. Okay. Let us define now the Euclid I.47. Can we get it this one? Just I.47, okay? Euclid I.47. Okay, Euclid I.47 is in the book of elements. Book of elements of number 47. Now, Euclid says that in a right angle triangle, the square of the side opposite is equal to the square of the side opposite of the right, of the right angle of the right angle is equal to the square of the sides, is equal to the sum of the square is equal to the sum of the square on the sides containing the right angle. Okay, this is very clear. In a right angle triangle, the square of the side opposite of the right angle is equal to the sum of the square on the sides containing the right angle. That is Euclid I.47, book of elements, number 47, proposition. Okay, now how we can justify this proposition? Though based on these samples, case number 2, we're going to modify on this. Say, on this one here, this is A and this is B. Okay, now let's see this, expand this one here to another as defined this one by Euclid. You see how the proportion of this one, if you will put this one A, B, C, okay, A, B, C. Now we will see A, B, C, D, E, F, J, H, I. Okay, see, look at on this one here, we'll see this one here, this is the middle. Now you remember this one, this is the substation. This is the wall of the substations. So this is the Y. If you just put this one Y, Y is 4. Okay? And this is the X. X is 3 meters. Now, we will add on this one, according to Euclid I.47, is if a particular triangle, right angle, yes, this is right angle, all of this one here, you see, this is 90 degrees. If you look at also, this is 90 degrees also. Now if you look up this one here, you see B, C, and A is a right triangle. B, C, and A, if you look up on the geometry, B, C, and A is a right triangle. So, this one here, okay, now CA is equal to the sum of CB and BA, okay, so they are equal. So we meant to say, if this is the length of this hypotenuse, this is X, we will see on the other hand also, we are going to put this one as a length, so this one is as a length also, okay. On this length all here, we could get this one, that the square of the side opposite of the right angle is equal to the sum of the square. You see what, imagine on this one here, they are on the rectilinear plane. On the rectilinear plane, CB is on the spot, no? On the plane of CA, he is on the spot with CH, okay? So, and you could see also, could imagine also GA, GA, and if you are going to expand it more, no, so that it would be perpendicular, go like this here. Okay, expand it. So that yeah, so that it would be look straight. Okay. Okay, so this one here, CA is its shape. And look at on this one here. GB has a right angle also on that one here. And going this one here to A, you could see also here that it could be angle. It has an angle. So GB and BE were said also a right angle. GB can also get this one also with an angle also BE. And he is also in the same plane also, the same line. So you see how GB would interact also with the same line with the, this is perpendicular also with the CB and is in line also, rectilinear plane. Is also in the side also of CH. So it says it is on the right angle equal to the sum of the square of the sides containing also on the right angle. So it justified that Euclid I.47 denote us that the right angle CBA, that CA, the square of this CA is equivalent to the square of this CB and BA. Okay, on this one it corresponds to the sum of this square and of this side also of this square of BA. So this is the side of it. Let us take for example, this is the A1 square, and this is the A2 square, and this is the A3 square for H, B, and H. They are all equivalent with the same square and also with the same right angle also. Okay, now let us see on this one how that corresponds with the Pythagorean theorem. Now on the Pythagorean theorem, let's see here that the x and y, we have x and y, and we have the length. We have the length here. Length of this ladder and length of this one is still the same, perpendicular, horizontal, this one here. So let's see this length, just like what we did also in Pythagorean theorem, that the C, this is B and this is A, C squared equal to the summation of the two sides, square of the sides. So C square root of A squared plus B squared. Okay, now let's say on this one here, length squared plus x squared plus b squared. Now let's go here, length square root of, what is x? X is 3 plus b. We have here. So we have length is 9 plus 16. So it brings us this one here with 34. Excuse me. So square root of 34. So square root of 34, we will say this one the square root of 34 is 5.83. So the length of this one is the length is 5.8 Hi, to continue with our calculations, we are all considering about how this x plus dx, it becomes the x now is, we have here is 3. So we consider this one plus 1, so we will get this one is 4 meters already. So the new height now, the new height which is y, so it will be y prime. So the y prime on that, no? The y prime, because this is the ladder. Now so we say on this one here, with this corresponding 4 meters on that, let's say with this Pythagorean theorem left, we have, can we use this one in y minus dy square on that, then let's use on that minus dx squared. So this is x squared before, huh? So we have L squared. The L squared here we have 5.83 square on that. Then we have the x squared, 4 meters. This is another height. So it could be 16. 16 I think. 4. So 16. Yeah. So here 4 squared. Okay. Now this back here 5.83 square minus 4 square. Then this back here, getting with this dy here 5.83. Let's cross and with let's simplify this one first. So 5.83, we have 5.83 square. That will give us 33.98. Then we have 16. Okay. Then we have y. Dy here. Y here. Y is what do we say here? Okay. Let's say y dy here 33.98 minus 16. So it will be here 33.98 minus 16. That could bring up as this one square root of 17.98. So square root of that one is, it could be 17.98. With a 4.24. So if y, we will say this one dy, this one if y is 5, if y is 4, let's say 4 minus 4.24. So the dy is 4 minus 4.24. We have 0.24. Okay, 0.24. Shall we say? Now if we increase x, if we increase x plus dx with 1 meter, it's good because like this here. We have also an increase also, a decrease also of dy. So that would happen on this one that we have come up this one here with, we are going to asked what are the ratio that on the beginning of our discussions on this chapter, we're asking how we could simplify, how we could determine the ratio on that. Now on this ratio we have here dy, dx. So it remains to say that we have here the dy is 0.24. So this is the ratio. Okay, this is the ratio of dy over dx, where dx, when we increase this one with 1 meter, so 0.24 and 1. So this is the ratio that we're being in. This is the function when we find a differential coefficient of y with respect to x. So 0.24 over 1. So that is the ratio on that. So so this is the height on that. So when we increase, which we increase the 1 meter on that ladder, the tenth also try to reduce also the height. So this is the new height now. This is the new height. So I'm talking the new height is the y prime. Okay? This is the y prime. Now, I think it's very clear for you also the justifications of how we could come up with these calculations. Now, let us see how we could get an expression, shall we say, we have been already subjective, we have been implied already, so that we call this an implicit function. Implicit functions, as we have known that one already, although, but that is the standard form. That is the standard form already in an angle. Even just like mentioning that it just implied already, implied functions. Shall we say on this one here, this is with this one we understood that this is with respect to y over x, this is a tangent. So say, so we are trying to get how the relations of x when y varies together. So that is the purpose of this chapter, relative growth. We determine, we adjust a little bit of dx, then the dy also, the y also in that proportion portion on that has just come up also with a particular amount, a little bit of that amount. What would happen that is this the ratio of that one came up with dy over dx. What happened in that ratio is 0.24 over 1. Okay. Now take a look on this triangle, this angle. So this is, shall we say, this is opposite already in a particular angle, triangle. We can see that it's definite, this one here. We could see, if we'll put this one theta, we'll represent this one, this is a tangent already. Theta with respect y or a over b. Or so we call this one x or y, excuse me, y over x, or the length of the ladder. So we'll put this one here on this. This is, we call it implicit function. Okay? Implicit functions is this one. If you have the tangent of theta, this is already implied. This is understandable already. So when we have a functions of this, so with respect of y, tangent theta times x. So when we go across this one here, x, okay, x tangent of theta over y. So we have here the corresponding to this one here. Okay? Tangent theta to go like this one here. Okay? So shall we call in this one is implicit functions. Now for those functions we have here on this growth, we were talking about this relative growth, talking about these variables and the constant. Here we are implying also these explicit functions. Those we cannot expect. Those we have not mentioned that is against the rules or it is following with the standard form. So we just putting this one as an explicit functions. Shall we say on this one here, x squared x squared x squared minus plus 3 plus 2y minus 7. So we could get here, if we put here x squared, so 7 plus 3, see here, plus 2y. So we put here on this x, that would be here 10 over 2y. So if we will with respect to the ax, this would be is equal to 10 square root of 10 over 2y. So that would be for this one is explicit function. So with respect to 2y, so we say, so let's say go like here, negative 2y, let's say minus 7 minus 3. Then we have here also plus x squared. Now, if we are going to put here negative 10, we have negative 2y plus x squared. If we are going to put this one here, negative 10. So, with respect to y, here negative 10 carried by 2, then plus x squared. So be informed that we have negative here, and this one also would become positive. So y, then we go like this 5 plus x squared. So this is the implicit function with respect to the y, 5 plus x to squared side. So this is explicit functions. So this is what we're going to derive on this one on the on relative growth. Thank you so much for watching.